Good evening to all. So, am I audible? Can anyone mention? Am I audible? Can anyone mention in the chat box? Is my voice audible? Okay then. Okay. So, in yesterday's class, I wanted to discuss the theoretical calculations for both Kirchhoff's voltage law to verify Kirchhoff's voltage law and Kirchhoff's current law, but I couldn't complete that. So today I will discuss the theoretical calculations for the laboratory manual, which is already available in my channel for the verification of Kirchhoff's voltage law and current law actually, but voltage law I have already discussed in previous session. So in this session I will discuss the Kirchhoff's current law. Okay. So same circuit I have taken, what I have discussed in the previous session, same circuit, theoretical calculations to verify KCL for the given circuit. So 1 minute, here I have written VC. Okay, so same circuit. So if you want, you can draw this circuit to verify theoretical calculations for Kirchhoff's current law. To verify Kirchhoff's current law, you can draw this circuit, whoever wants to draw it, so that you can also do the calculations along with, as I'm explaining, you can write it down in your notes. So just draw it, I'll give you a minute. So meanwhile, I'll just explain. You can, so since we have to verify Kirchhoff's current law, what we have to consider here is, we have to check for the nodes. Okay, we have to check how many nodes are there here. So for that, first of all, let us see, let us check the current sources. So I'm sorry, what are all the sources that are available? There can be current source or voltage source. So if you carefully observe, here there is a voltage source whose value is 30 volts, notation by you have assumed as V2. Another voltage source is there, okay, whose value is 30 volts and notation is V2. So we have two voltage sources, okay, and both voltage source voltage values are same, that is 30 volts. Now from this positive terminal, okay, current will start to flow into the circuit. Okay, from this positive terminal of this V1 source, current will start to flow in this direction. So after reaching at this point, what will happen? Current will divide. Okay, current will divide. Now this current will flow. I'm sorry, my cursor. This current will flow like this. This current, it is flowing like this, it is flowing like this, and from this source, from positive terminal, current will come out and it will flow like this, it will flow like this, and this current, it will flow like this. Both the currents at this point, what will happen? They will add up. Okay, they will flow like this, and at this point, what will happen? These two currents will add up and they will flow through this R2. It will flow through this like this, and at this point, what will happen? Current will once again divide, and it will return back to V2, and this current will return back to V1. Okay, so based on the arrow marks that I have mentioned, what we can see here is, from the source V1, I will just take the laser, from the source V1, current starts to flow, okay, and at this node, current is dividing. So since current division is taking place, this is a node, okay. This is one node. Let us check for number of nodes here in this given circuit. Now this current flows like this. Okay, from up to here, from this positive terminal, current flows like this. At this node, both the currents are meeting and they are adding up and they will flow in this element R3. So here currents are adding up, two currents are entering the node, one current is leaving the node. Okay, so this is also a node. Okay, because currents should either add or current should either divide at a node. Now from R1 current will flow like this, from R3 current will flow, both the currents will add up here and the added current will flow through R2. So this is also a node. Okay, now current will flow through R2. At this point what is happening? Current is dividing and one part is going back to V1, another part is going back to V2, negative terminals. Okay, so current is returning back to the sources. So from whichever point current adds here, one current is entering, other two currents are leaving. So this is also a node. So now how many nodes are there total here? I will take a pen. Total how many nodes? This is one node. This is another node. This is another node. And this is another node. Total 4 nodes are there. Total how many? 4 nodes are there. So how to decide whether a point is a node or not? Wherever current adds up or current divides, that point you can call it as a junction or node. So here current is at these 4 nodes, current is either adding up or current is either dividing. So we can modify this circuit. I hope you have drawn. Meanwhile, you have drawn this circuit. I will erase all the arrow marks. Okay, I hope you have drawn. As soon as you complete, if you are copying it down, as soon as you complete, you can mention in the chat box. Okay, you can mention in the chat box so that I will change the slide. So this is it. Now I have assumed node 1, instead of writing 1, I have written A. This is my node A. Node B, you can write, your notations are your wish. Node C and node D. Earlier, if you remember in the previous slide, what did I write? I wrote 1, 2, 3, 4. Okay, your wish. If you want to write 1, 2, 3, 4, write 1, 2, 3, 4. If you want to write A, B, C, D, you write A, B, C, D. Your wish. Notations are our wish. So you can, in the same circuit which you have drawn just now, you just mention the nodes and write A, B, C, D. Okay. So if you see at D terminal, what is happening? From here current is dividing at this node and it's not terminal, it is the node. D is the node, okay, not terminal. So at this node D, current is dividing and return back to the negative terminal of V1 and another part of the current is returning back to the negative terminal of V2. Okay, so from whichever node current return back to the sources, that node usually you will call it as reference node, and reference node value will be always 0. Reference node value will be what? How much? It will be always 0. Okay. Reference node value will be always 0. So that's why I have put a ground symbol here. This is the ground symbol and I have mentioned 0 volts. Okay, I have mentioned the 0 volts. Now, if you forget about the reference node, how many nodes are available here? If you forget about the reference node, how many nodes are available? Total 3 nodes. What are those nodes? Node A, node B and node C. Okay, total 3 nodes are there. Okay, so I didn't consider reference node. Why? Because we know node voltage at reference node is always 0. So I didn't consider that. I just wrote 0 volts and I forgot about it. So total 3 nodes are there, A, B, C. So 3 nodes are there, therefore we can assume node voltages. Okay, we can assume node voltages. So what you can do is you can write in the same diagram, no need to draw again and again. I am showing you different parts, but in the same diagram we can perform all sort of modifications whatever I am doing. So now what you people do is mention node voltages. Where is node voltages? Separately I didn't draw any node voltages circuit. It is there actually, but I think I have missed it. I might have deleted it unfortunately. So what you do is in this this circuit, okay, I just copy it. I'll just copy it and I will write the node voltages. Yeah, it is already there. It is already there. So simply what I want is node voltages. So write V. Here I can write V. Okay. This font size I will increase. Okay. So I have written V here. I will just copy it. I will just copy it and I will just place it wherever I want. Huh? Okay, I have to select this. Okay. Okay, I will just copy it and I will paste it somewhere. So this is V suffix A. Okay, V suffix A. Next once again I will paste it and this is my V suffix B. And one more I'll paste it V here. So here I couldn't write V suffix C. I will just modify this. So simply I will just 1 second. I will just place it here. V suffix C. Okay. This is V suffix C. Okay. So VA, VB, VC. I'll just copy it and paste it in one of the slides. So you people, wherever you have written ABC, you instead of ABC, you just write VA, VB, VC. Okay. So mention the node voltages. Okay, mention the node voltages. I have mentioned VA, VB, VC, and this is my reference node 0 volts. Okay, no need to draw again and again. You people just do the modifications in the same circuit. So VA, VB, VC, and 0 volts. Okay, we have mentioned the node voltages now. Now we have to mention the currents. Okay, at each node, current directions at each node. So if you carefully observe. If you carefully observe at each node, I will take the pen. At each node, at this node, how many branches are there? One. Here, how many branches are there? This is one branch. This is one branch. This is one branch. So at node A, 3 branches are there. At node B, this is one branch. This is one branch. This is one branch. Total 3 branches at node B. At node C, how many branches? 1, 2, and total 3 branches. So at each node there are 3 branches. Forget about the reference node. We already know reference node voltage is 0 volts, so no need to consider branches and all. Okay. So there are 3 branches connected to each node. Node A, node B, and node C. What is the node voltages? VA, VB, and VC are the node voltages. Now consider the branch currents. One thing, you just observe carefully. This is my source V1. Okay. It is directly connected to node A. Okay. It is directly connected to node A. So what is the voltage at node A? VA. So since source is directly connected to node A, V1 will be equal to VA. Why V1 will be equal to VA? Because source is directly connected to node. So node voltage is nothing but source voltage. Okay. Node voltage will be nothing but source voltage. Why? Because the source is directly connected to the node. So VA is nothing but V1. VA is nothing but what? V1. Okay. So now let us assume the current directions. Your wish, you can assume any current direction. So see here what I have assumed. Since node source is directly connected to the node, current coming from the source, since this is V1, I have assumed current as entering current here, that is I1. So from the source, current is the node voltage is nothing but VA is nothing but V1, that is 30 volts. From the source, current will divide into I4 and I3. Let us assume notations are our wish. So I am dividing it into I4. I1 is divided into I3 and I4. Okay. So I1 is entering current, I4 and I3 are leaving currents. Similarly, okay, similarly at node B, so you can see 3 branches. I have assumed all the currents at node B leaving. Okay, so here all the currents are leaving at node B. Similarly at node C, I have assumed all the currents leaving. Your wish, you can assume at all nodes, all the currents either entering the node or all the currents either leaving the node. Okay, all the currents either leaving the node, your wish. See, if at node A I have assumed current is entering and one current is entering, 2 currents are leaving. Actually, no need to assume current directions at node A. Why? Because already source is directly connected to node A. So we already know the node voltage. Okay. So we already know the node voltage. Therefore, no need to connect. No need to mention the current direction because no need to verify Kirchhoff's current law at this node. So, but I have mentioned the current directions. Okay. But it is not necessary to mention the current directions here, but I have, because we need to determine current flowing through R5 and we need to determine current flowing through R3. That's why I have mentioned I4 and I3, and I have assumed that source current, of course, some notation I1. So similarly at VB, I have assumed 3 currents. See, this is the I3 current which is traveling from node A to node B. Similarly, if current travels from node B to node A, same I3 current will flow, but direction will change. That's it. Okay. So in the same element, 2 different currents cannot flow. If this is I3, I should not write this is I5 or I6 or I7 or I8. Okay. In the same branch, whatever the current direction, you must mention same notation for the current. Okay. Similarly, at node C, I have assumed all the currents are leaving. So all the currents are leaving. So I2 current is leaving node C, I5 current, I4. See, this is I4, this is also I4. So make sure if there is an element, okay, if you are mentioning 2 directions at its terminal, see, this I4 are opposite to each other, isn't it? So if you are mentioning 2 opposite current directions, their notations should not change. This is I4. This is I4. You should not change the notations. Okay. That you should make sure. See here. I3 current. I3 currents. Notation I did not change. Even though current directions I might have changed. Okay. I did not change the notation. Similarly across R3, I5 current I have mentioned. This I5 current directions you see they are opposite to each other. Okay. But notation I have kept it as it is. Okay. Notation I5 I have kept it as it is. So this is it. At each node. Okay, you have to assume either all currents are entering or all currents are leaving, or you can assume some of the currents are entering and some of the currents are leaving. At node A, what did I assume? 1 current is entering, 2 currents are leaving. At node B, what did I assume? I assumed all the currents are leaving the node. At node C, I have assumed all the currents are leaving the node. So if you don't like this, you no need to follow me. You can assume your own directions. Depending on the current direction that you have assumed, you must write the nodal equations. Okay. So did you complete? Did you draw this? No need to draw, isn't it? You might have mentioned the arrow marks. Okay. In the same diagram, you must mention the arrow marks and write the current notations. Okay. I hope you have completed. Okay. As I already told you, now since we have current directions here at each node, now let us apply KCL at each node and write the nodal equations. So but remember at node A, no need to write nodal equations. Why? Because source is directly connected to the node. Okay. So that's why let us go to the next slide. Okay, at node A. So at node A, what is it? I didn't take the pen. So at node A, V1 is directly connected to what? Node. Therefore, node voltage is equal to the source voltage. So VA is equal to V1, that is equal to what? 30 volts. VA is equal to V1, that is equal to 30 volts. Now, based on whatever current direction that I have assumed some current direction, isn't it? One current, I1 current is entering, I3 and I4 currents are leaving. So, if depending on which direction current is flowing, either you can add them or subtract them. So, I3 current, I4 current directions are same, isn't it? I3 current, I4 current are leaving, means their direction is same. They are leaving currents. So, leaving currents, sum of leaving current should be equal to sum of entering currents. How many entering currents are there? Only one entering current. Where is my cursor? Yeah, only one entering current is there. Only one entering current, that is I1 is there. And how many leaving currents? Two leaving currents are there. Both are leaving. I3 and I4 are leaving. So add leaving currents. Algebraic sum of leaving current should be equal to algebraic sum of the entering currents. There is only one entering current. So write the entering current I1 is equal to I3 plus I4. That is, consider it as equation 1. Okay. Consider it as equation 1. Now, let us apply KCL at node B. Okay, let us apply KCL at node B. Let us apply KCL at node B. So, we have assumed, what did we assume? We have assumed all currents are leaving. All currents are leaving. No current is entering. So, algebraic sum of all leaving currents must be equal to 0. So, what are all the currents at node B? I will just copy that image here. See, what are all the currents at node B? What are all the currents? I3, I6 and I5 all are leaving. So, algebraic sum of leaving currents. Only leaving currents are there. So, algebraic sum of all leaving currents is equal to 0. Okay, since all are leaving currents. Okay, so all the currents are leaving. So, you just add all the currents. Okay, so I3 plus I5 plus I6 is equal to 0. Okay, so what is I3? What is I3? Okay, I might have kept that circuit as it is. Where is my circuit? Is there? Okay, I'll just minimize it. I will take the smaller image so that it will be easy to explain. So let us see. Now see, what is I3? I3 is equal to what? I3 is traveling from, I3 is the current. I3 is the current which has started from we have considered which node? We are at node B now. Okay, we are at node B. So at node B, current I3 current travels from VB to VA. Isn't it? It is traveling from VB to VA. So what is the resistance through which I3 current flows? Resistance through which I3 current flows is R1 resistance. So what is the I3 current value? I3 is equal to V by R. What is V? V is the potential difference across R1. What is the potential difference across R1? Since we have considered node B, so VB minus VA by R1 value. Okay, VB minus VA by R1. Okay, that is our equation. One of the equation of current equation, I3 current. Similarly, let us consider I5 current. What is I5 current? I5 current, it is traveling from VB to VC. I5 current is traveling from Okay, so let us see. Someone is asking whether I have had my supper or not. Until this class is over, I will not have. I am already hungry from 6 p.m. onwards. I am hungry. I didn't eat anything. I'm really hungry. So I can't do anything. Okay, my daughter is laughing. So I5 current, let us see. I5 current is traveling through which resistor? R3 resistor. So what is the voltage across R3 resistor? This is the terminal voltage of R3, isn't it? VB, and two terminals of R3 are VB and VC. So difference of terminal voltage by R3 will give us the I5 current. So I5 is equal to what? It is traveling from VB to VC. Therefore VB minus VC by I5. VB minus VC by R3. Sorry, not I5. We are determining I5 current, isn't it? So I5 is equal to what? VB minus VC by R3. So I5 current is traveling from where? We have considered node B. So I5 current, it travels from where? From VB to VC. Okay, terminals of R3 are, one terminal is VB, another terminal is VC. So differential voltage, what is differential or potential difference? Potential difference across R3 is what? VB minus VC divided by R3 value. Okay, so I5 is VB minus VC divided by R3. Similarly, I6. Okay, now let us see what is I6 current. Okay, what is I6 current? This I6 current travels from where? From node B to reference node. Okay, it travels from node B to reference node. So what is the resistor through which I6 current travels? It travels through resistance R2. Okay. Okay, it travels through resistance R2. So what is the voltage difference across R2? What is the terminal voltage of R2? One terminal voltage is VB, another terminal voltage is reference voltage. What is reference voltage? 0 volts. Okay. So where did the current start? From VB. Therefore VB minus 0 divided by R2. I6 is what? VB minus 0 divided by R2. Okay. So I hope you have understood. This is I3 equation, I5 equation and I6. Anyone, if you want me to repeat, you just mention repeat in the chat box so that I will repeat. I will just remove this image. Okay, you can consider these three equations as equation 3, 4 and 5. Okay, so this is our equation 2, above equation. This is equation 2. Okay, and current equations I3, I5 and I6. Okay, equation 3, 4 and 5. So just I will give you a minute. You can write it down if you are copying it down. So I hope you have written. Now substitute 3, 4, 5 in 2. Okay, what you have to do? Substitute this 3, 4, 5 in what? In equation 2. So if you substitute 3, 4, 5 in equation 2, what do you get? This is what you will get. Okay, I3 is what? VB minus VA by R1. I5 is VB minus VC by R3. I6 is VB minus 0 by R2. So what is VA? VA is nothing but V1. V1 is what? 30. Okay. So VB minus 30. Okay, erase. I want to erase all links. Okay. So what is VB minus? I will take the laser. So VB minus VA by R1. So VB minus VA we already know. VA is nothing but V1. So substitute 30. R1 value is how much? 2000. VB VC we don't know. So VB minus VC by R3 is 1000. VB minus 0 you can write as VB. R2 is 1000. Okay. You can mention 1000 here. So you just replace R1 R2 and R3 values in their respective places, and instead of VA write V1. V1 is nothing but 30, so I have written directly 30. If you see in the denominator, there is 2000, 1000 and 1000, isn't it? There is 2000, 1000 and 1000 in the denominator. So you can take 1000 common. If you take 1000 common, what do you get? VB minus you just take 1000 common and send it to the right side. It will become 0, isn't it? You just take 1000 common here in this equation. Take 1000 common and send it to the right side. It will become 0. So what is left over? VB minus 30 by 2 plus VB minus C by 1 plus VB by 1. So 1, is it required to write 1 in the denominator? No need. But I have written. Okay, I have written. Of course, I have written, but no need to write it, isn't it? Okay, no need to write denominator. In the denominator, no need to write 1. But I have written here because I have to give. I am explaining, so I thought it will be better to give step-by-step explanation. So, if you complete, you can just mention in the chat box. You can just at least type C. If you type C, I will understand you have completed. My voice is not audible. Please check your earphones, because I have also joined my own class with my mobile, and in my mobile I am able to hear my voice clearly. Anyone else, if my voice is not audible, please mention, because in my mobile I am able to hear my voice clearly. So in order to know what's going on and in order to read the chat messages, I connect myself as one of the audience. Anyone else? Can you please mention whether my voice is audible or not? Someone has mentioned my voice is not audible. Is my voice audible? Can anyone mention in the chat box my voice is audible or not? You have completed, okay? Okay, I have changed this slide, but am I audible? Can anyone mention in the chat box? Audible? Okay then. Please, whoever is unable to hear my voice, please check your earphones whether you have connected it properly or not, because I am also one of the audience. Okay, I am also one of the audience in my mobile. So I am using laptop. I am using 2 laptops at a time here. Okay, and I am also using my mobile here. So see, I have just expanded the above equation. If you expand the above equation, what do you get? VB by 2 minus 30 by 2 plus VB minus VC plus VB equal to 0. Just expand the above equation. So you will get VB by 2 minus 30 by 2 plus VB minus VC plus VB equal to 0. VB by 2 means what? 0.5 VB minus 30 by 2 means 15 plus VB minus VC plus VB. VB plus VB, you can see you have 3 VB terms, isn't it? 0.5 VB plus VB plus VB. So 2.5 VB minus VC is equal to minus 15. I have sent it to the right side. So this is 15. So 2.5 VB minus VC equal to 15. That is equation number 6. Okay. Consider it as equation number 6. I hope you have completed, isn't it? If you have completed, please mention. I will just change this slide and apply. I will apply KCL at node C. Okay, I am changing this slide. Now, let us apply KCL at node C. Okay, at node C, I will just copy that image. Image means circuit. Where is it? So at node C, if you just observe at node C, all the currents, what did I do? What did I assume? At node C, this is my node C, isn't it? Node voltage is VC. Okay, node voltage is V. How are the currents? All the currents are leaving the node. They are leaving the node. They are moving away from the node, isn't it? All the current, these three currents are moving away from the node, means they are leaving the node. So, what are all the currents at node C? Currents are I2, I4 and I5. All are leaving. So, algebraic sum of leaving currents is equal to algebraic sum of entering currents. Here I have assumed all the currents leaving. So, algebraic sum of leaving currents is equal to entering currents at 0. So, equal to 0. So, I2 plus I4 plus I5 is equal to 0. Now, let us determine each current. Okay. At these three currents are there at node C. Now, let us write down the current equations. That is nodal equations, you can say. They are not nodal equations. We are not applying KCL, of course. So, each current equation, I2. So, where is I2? This is I2. I2 is traveling from where according to this diagram? I2 is traveling from VC to V2. Isn't it? It is traveling from I2 current is traveling from VC, node C. Okay, VC is the node voltage. From node C to V2. So, it is traveling from VC to V2, I can say. What is the resistor through which this I2 current flows? It is R4 resistor. Okay. So, what is I2? VC minus V2 by R4. I2 is what? VC minus V2 by R4. Similarly, I4. So, what is I4? What is I4? I4 is the current that is traveling from VC to VA. I4 is the current which is traveling. Now we are at node C, isn't it? We have considered which node are we at? We are standing at node C. Okay, we are at node C. So the I4 current will travel from where? From VC to VA. Okay, I4 current. So what is the resistor through which this current will flow? I4 current will flow. Resistor is R5. Okay, through R5 the current I4 will flow through resistor R5. Okay. So now what is the terminal voltages? Okay, across what are the terminal voltages of resistance R5? What are the terminal voltages? One terminal voltage is VC, other terminal voltage is VA. But we are at which node now? VC node C. Therefore, I5 is equal to what? VC minus VB. Not VB. It's I5 is VC minus VA, not VB. Sorry, I think VC minus VA by R6 I have written. Why R6 is not there? 1, 2, 3, 4, 5. Only 5 are there. So here RC VC minus this I4. Once again, yeah. What is I4? I4 is VC minus VA by R5. This is R5. So once again, this R6, by mistake I have written R6, I will change it to R5 once again. This is it. I4 is what? Vc minus Va by R5, and I5 is Vc minus Vb by R3. Yeah, now it is correct. I will just save it. So what is it? I4 is what? I4 is what? I4 is Vc minus Va divided by R5. Okay, Vc minus Va divided by R5. And what about I5? I5 current is traveling from where? From Vc to Vb. Okay, from Vc to Vb. I5 current is traveling from I5 current is traveling from Vc to Vb. So what is the resistor through which I5 current travels? R3 resistor. Okay, it travels through R3 resistor. So what are the terminals of R3? Vc and Vb are the terminals of R3. And since we are at node C, so what is the I5 current? Vc minus Vb by R3. Okay, Vc minus Vb by R3 is our I5 current. Now mention the just give some numbering to this. So I2 plus I4 plus I5 is our equation number 7. Consider I2 current equation as 8. Consider I4 current equation as 9. Consider I5 current equation as 10. Okay. So if you are writing, if you are completed, please mention. You just mention C. Okay, completed. Okay then. Now substitute what? Substitute 8, 9, 10. In which equation? Equation 7. Write down. Next step is what? Substituting 8, 9, 10 in equation 7. So substitute it. If you substitute 8, 9, 10. Now substitute 8, 9, 10 in equation 7. If you substitute 8, 9, 10 in equation 7, what do you get? Instead of I2, what you should write? Vc minus V2 by R4. Instead of I4, Vc minus Va by, again, I have simply copied, it seems. From previous slide, I have simply copied. This is 5. Okay. By mistake, I have written 6. Okay. So this is Vc minus. Okay. This is our I2 current, that is Vc minus V2 by R4. I4 current is Vc minus Va by R5. I5 current is Vc minus Vb by R3. Okay, that is it. Now, if you observe here, we already know V2 value, that is source voltage 2 value. We already know Va value. Why? Because Va is nothing but V1. V1 value is how much? 30 volts. V2 value is also 30. So, in the next step, Vc minus 30 by 1000. This is it. Vc minus 30 by 1000. Next, Vc minus 30 by 1000. Next, Vc minus Vb by 1000. Okay, R4 value is 1000, R5 value is 1000, and R3 value is also 1000. Okay, R4, R5. Okay. Okay, now if you observe, in the denominator of all these equation, what is there? Common denominator. What is it? 1000 is there. So take 1000 common and send it to the right side. It will become 0, isn't it? Take 1000 common in this equation. Take 1000 common and send it to the right side. It will become 0. So what is left over? Vc minus 30 plus Vc minus 30 plus Vc minus Vb is left over. Okay, denominator terms you can take common and send it to the right side. Now Vc minus 30, Vc minus 30 and Vc minus V is left over. Okay, Now here one VC is there, another VC is there, and another VC is there. All these three VCs are positive. And what else is there? Minus VB is there and minus 30 is there. So what I have done? I have written minus VB plus 3 VCs are there, all are positive. So 3 VC is equal to minus 30, minus 30. 2 minus 30s are there. Those two minus 30s you add it, you will get minus 60. Send that minus 60 to the right side. It will become positive plus 60. Okay, this is plus 60. Consider it as equation number 11. If you have completed, please mention. So I hope you have completed. I am just changing this slide. So now solving equation 6 and 7. So what is our equation 6? 2.5 VB minus VC equal to 15. Equation 11 is minus VB plus 3 VC is equal to 60. Now in the scientific calculator, you can see mode button. If you don't know how to operate substitute, you just substitute these two equations in the scientific calculator. So if you have a scientific calculator, you just take it in your hand. In that you can see mode. You just press the mode, and if you press the mode, you can see 1, 2, 3, 4, 5, 6, 7. Some numbering you can see, and besides to that, what you want to write, that is mentioned. So if you in the mode, when you press mode button, if you see number 5, besides to number 5, what you can see? EQN. EQN. Okay, in the calculator, okay, in the scientific calculator, you can see number 5. Besides to that, you can see EQN means equation. Okay, so press number 5 in your calculator. So first of all, take the calculator, turn on the calculator. After that, press mode button in your calculator. There will be mode button in your calculator. Press mode button in your calculator. After that, when you press the mode button, you can see some 1, 2, 3, 4, 5, 6, 7, 8 numbers. Okay, and besides to the numbers, what is their operation, for what purpose those numbers are to be pressed is mentioned. You just press, if you see number 5 will be there, besides to 5 it will be EQN will be there. So you people just press 5. So okay, after pressing 5, what you have to do is, you just first of all type 2.5. After that type minus 1. After that type 15. Okay. And after that type minus 1. After that type plus 3. Plus 3 means just simply type 3. After that press 60. Okay. So after pressing each number, you must press enter. Okay. So after pressing each number, typing each number, you must press enter. At last, when you type 60 and you press enter, enter means equal button. Okay. In your calculator, equal to button will be there. So you just press the equal to button. So when you press the equal to button, automatically VB value will be displayed, as well as once again when you press the equal to button, next time VC value will be displayed. Okay. So if you just go through the calculator. Okay, you just take the calculator and try to substitute these two equations in the scientific calculator. When you substitute, and if you press the equal to button there, first time you will get VB value, that is 16.15 volts, and once again when you press the equal to button, you will get 25.38 volts. Okay. So VB value and VC value directly you can get it from the calculator, or manually also you can do it. You people in your intermediate or in your school age, if two variables are unknown, how to simplify them, you might have already learned. Okay, but after joining BTech, you people, for some calculations, if we are doing them manually, it may consume some time. So it's better to use the calculator instead of doing them manually. Manually also you can do it, and you can determine VB value and VC value. Now what is VA value? VA is already known. VA is nothing but V1. VA is nothing but V1. That is equal to what? 30 volts. What is VB that we have got just now? 16.15. What is VC that we have got just now? 25.38. Okay. So consider VA as 12, equation number 12, VB as equation 13, and VC as equation 14. Okay. So I hope you have written. I am just moving to the next slide. Now we know node voltages. What are our node voltages? VA, VB, VC. VA is 30, VB is 16.15, and VC is 25.38. So now let us let us determine current I3. Okay, what is our current I3? It is our equation 3. So what is current 3 equation? VB minus VA by R1. What is VB? Okay, VB is our what is VB? That is 16.15 and VA is 30. Okay, so VB 16.15 minus 30 by what is R1? 2000. Okay, you just solve it. You will get I3 value, that is minus 0.006925. So that is 25 amperes. This is amperes. I didn't write amperes here. I must have written. I'll write the amperes. I'll just type the amperes here. This is ampere, this is amperes. Okay, so these amperes you can convert them into milliamperes. I3 value is how much now? Minus 6.925 milliamperes. What is meant by minus? Here you have got negative value. So I3 is negative. That means that actual current direction is opposite to the assumed current direction from node B. Okay, so I3 current direction, what you have assumed is opposite to the actual current direction because of the source. Okay, so because of the source, the current direction that you have got here, the assumed current direction is opposite to the actual current direction. So simply you can you can write it down below in one statement that I3 that I have assumed, the direction of the I3 current that I have assumed in the given circuit is opposite to the actual direction of the current direction in the given circuit. Therefore, actual current direction in the given circuit, therefore I3 is equal to 6.925 milliamperes. No need to write minus. Okay, so that you can mention there. So I hope you have completed. So already it is approximately 50 minutes are over, I think so. So that's why. So I hope you have completed. I am moving forward. Now let us determine I5 current. Okay, let us determine I5 current. So what is our I5 current equation number? I5 current equation number was I5 current equation number was 10. Equation number was 10, but I have not changed it here. I5 current equation number was 10. Okay, so let us determine I5 current whose equation number earlier was 10. I did not change the equation number here. So equation number is not important. So I5 current equation, we already know what is I5 current equation. I5 is equal to what? VB minus VC by R3. What is VB value? Just now we have calculated. VB is 16.15 and VC is 25.38. So divided by R3 value is how much? 1000. You just simplify it using the calculator. Okay, if you simplify using the calculator, what do you get? Okay, minus 0.000923 you will get. Okay, so this is the current, isn't it? The current is in amperes. You will get the current in amperes. Okay, theoretically, of course, we are doing theoretical calculations. Okay, so I5 is what? I5 current is how much you are getting? It is 0.00923 amperes, of course, and you can see you have got negative current. That means what? The current direction that you have assumed is opposite to the actual current direction of the current flow in the given circuit. So you have assumed the opposite direction with respect to the current direction, actual current direction in the given circuit. So you just convert amperes into milliamperes. If you convert amperes into milliamperes, I5 is equal to what? Minus 9.23 milliamperes. Okay. Okay, now I hope you have completed. Now let us determine the current I6. Okay, so I6 equation was your equation number 5. I6 equation was your equation number 5, I6. So I6 is equal to what? VB minus 0 by R2. So what is VB? 16.15 minus 0 by R2 is 1000. Okay. So what is I6? It is, you just solve it, you will get 0.01615. You just observe here, you didn't get any negative value. That means whatever current direction that you have assumed for I6, that is the actual current direction in the given circuit. So if you get the positive values, that means whatever current direction that you have assumed, in the same direction current will flow in the circuit. So you just convert this amperes. I didn't write amperes. I will write amperes here. The current that you are going to calculate here is amperes. It will be in amperes. You convert that into milliamperes. If you convert that into milliamperes, this will become 16.15 milliamperes. So I6 is 16.15 milliamperes. You can give some numbering to these currents. Okay, here this current I have assumed it as, I have given some numbering to it. That is number 17. Okay. Okay, I hope you have completed. Now, I2 current. So, what is the equation of I2 current? I think it was the equation number 8. So, I2 equation is what? Vc minus V2 by R4. So, what is Vc? 25.38. What is V2? V2 is the source voltage 2. That is 30 volts. Divided by R4. What is R4? 1000 ohms. Okay, just simplify this. Okay, just simplify this. And what do you get? I2 is equal to, once again, I have to end this and I have to write amperes here. I did not write amperes. I wrote milliamperes, but I did not write amperes. So you just solve it. What do you get? I2. How much is I2? I0 is equal to minus 0.00462 amperes. So you just convert that into milliamperes. What you will get? I2 equal to minus 4.62 milliamperes. So what is the current? What is the current that you have got? You have got the negative current. That means what? I2 is negative. That means what? The actual current direction is opposite to the assumed current direction at node C. Okay? Actual current direction is opposite to the assumed current direction at node C. Therefore, actual current direction of I2 is 4.62 milliamperes. Okay, you can mention. Therefore, actual current direction of I2 is opposite to the assumed current direction. Therefore, I2 is equal to 4.62 milliamperes. No need to write minus here. So, I hope you have completed. So, I will try to conclude as quickly as possible. It's almost 1 hour. So, I will try to conclude as quickly as possible. Okay, now let us determine I4 current. What is I4 current equation? I think it was equation number 10. So what is I4? I4 is equal to what? Vc minus Va by. So once again, same thing I might have copied. Earlier I wrote R6. Same thing I might have copied. So it is not R6, it was R5. So by mistake I wrote R6. So what is I4? Vc minus Va by R5. I4 is Vc minus Va by R5. Okay. So it was our equation. I4 current is Vc minus Va by R5. It was our equation number 9, not even 10. Okay. So it was our equation number 9, I think. So once I will check and I will just change it. It is not important. Numbering is not important. But yeah, Vc minus Va by R5, it was our equation number 9, not 10. It was our equation number 9. You people just check if I have written these equation numbers there. That is not at all important actually. No need to mention equation 9 at all. Directly you can mention, write down the equation. So I have written excess content than required. So that it will be more easy to understand. That's it. That's the reason I have written this whole statement. No need to write this whole statement what I have written here above. No need to write. What is I4? VC minus VA by R5. What is VC? 25.38. VA means V1. That is equal to 30. What is R5? 1000. Using scientific calculator, you just solve it. What do you get? I4 equal to? You are getting negative value, isn't it? Minus 0.00462 amperes. Minus 0.00462 amperes. You convert that amperes into milliamperes. What will happen? I4 equal to minus 4.62 milliamperes. So I4 is equal to minus 4.62 milliamperes. Okay. So I4 is what? Negative. I4 is negative. That means what? I4 is negative. That means what? I4 is negative means the actual current direction in the circuit is opposite to the assumed current direction. Okay. So you can mention that statement. Now, so we have determined all the currents. Okay, we have determined all the currents in the given circuit except I1 current. I1 current, you know, I1 current is what? I1 current is the current that is coming out of this source V1. Okay, I1 current is the current that is coming out of source V1. So, what is I1 current is divided into I2 and I3 and I4. I1 current is divided into I3 and I4. Means I1 is equal to what? I3 plus I4. So what is I3? 6.95 and I4 is 4.62. So you just add those two, you will get the I1 current. Why we are not using nodal equations to determine I1 current? For all the other currents we have used nodal equations, isn't it? Here we are not using nodal equations. Why? Because there is no need to determine the node voltage at node A. Why? Because directly source voltage is connected to node A. Since directly source voltage is connected to the node A, no need to write node equations. Therefore, if you want to determine I1, simply by simplifying the circuit, you can determine I1 value. Okay. And it is understood. No, since voltage source is at node A, therefore the current will divide into two parts there. Two branches are connected to that node. And the other branch source is there. So simply add those two currents, you will get the I1 value. Okay, so now the calculation part is over. Now let us theoretically prove it. Let us see the theoretical proof. Within 5 minutes I will conclude this session. Okay. So theoretical proof. To verify what? KCL at node A. So at node A, no need to verify KCL theoretically. Practically you can verify, but theoretically no need. Why? Because you are not writing any nodal equations. But what is our equation? That in terms of current we have already written something. Simply I wrote I1 equal to I3 plus I4 because I1 is entering current, I3 and I4 are the leaving currents. And actually in the previous slide, if you remember, what did I write? I1 is simply I added I3 and I4 values to get I1. So once again I have written here same terms and I have got perfect 0. Okay. So actually theoretically no need to verify KCL at node A. Why? Because source voltage is directly connected. Voltage source, not source voltage. Its voltage source is directly connected to node A. But just for the namesake, I have written the theoretical proof at node A. No need to do that. Okay, within 2-3 minutes I will conclude. Within 1 minute maybe. Okay, so theoretically we have to verify KCL at each node. At node A, no need to verify, but I have written just for the namesake. So I hope you have written. Okay, now let us verify KCL at node B, theoretical proof for node B. So what are all the currents at node B? Algebraic sum of I3 plus I5 plus I6 is equal to 0. What is I3? Minus 6.92. What is I5? Minus 9.23. What is I6? 16.15. So add all the currents. What do you get? 0. So 0 is equal to 0 means what is it? KCL is verified at node B. Okay, KCL is verified at node B. Okay, KCL is verified at node B. Similarly, now let us verify KCL at node C. To verify KCL at node C. So what are all the currents at node C? I2 current, I4 and I5 current. So all these three were leaving currents, isn't it? Node C. So I2 plus I4 plus I5 is equal to 0. Okay, there are no entering currents. All currents were leaving. So I2 plus I4 plus I5 is equal to 0. So what is I2 current? Minus 4.62. I4 is minus 4.62. I5 is plus 9.23. Okay, so you add all these, you will get minus 0.01 up, which is approximately equal to 0. So algebraic sum of all currents are meeting at node, sorry, here I forgot to change. See, same statement if I have to write again and again, I will simply copy and paste it, and whatever modifications that I have to do, I forget to modify. So I just copied from the previous slide, algebraic sum of all currents meeting at node B equal to 0. Instead of B for this slide it is C, because we have written the currents for at node C. Okay, so it is C. I forgot to change it. So algebraic sum of all currents meeting at node C is equal to 0. Therefore KCL is verified at node C. Okay. So at reference node, no need to verify. Only at node A, node B and node C, we have to verify Kirchhoff's current law. So that we have verified. This is our theoretical proof for KCL. So theoretical calculations for Kirchhoff's voltage law. That video I already took that session earlier, live session earlier. If you have not attended that session, you can go through my channel. It is already available in my channel. Okay, so for this session was for verification of Kirchhoff's current law for the given circuit. Okay, so if anyone have any doubts, if you mention in the chat box, I can give answer to that. If you have any queries, any comments, if you have understood or not, please mention in the chat box. If you did you understand this calculations for the theoretical calculation for the circuit, which for which I have prepared the manual, and that manual is already available in my channel. Okay, so these are the theoretical calculations for the Kirchhoff's voltage. This is for Kirchhoff's current law, of course. For Kirchhoff's voltage law also, yesterday I took the live session. So both the theoretical calculations are for the manual, which is available in my channel for the verification of Kirchhoff's voltage law and current law manual. Anyone? If you have any doubts, any point which was not clearly understood by you, if you mention that, I will just explain it. You can mention in the chat box. Any doubts? Okay then. Okay then, I will conclude this session. If you have understood, you can click on the like button so that this video will be available to as many people, whoever wants to learn this concept. For them this will be useful. So you people can click on the like button so that others can also go through it, whoever wants to learn Kirchhoff's current law. Okay, thank you.